Hello guys, welcome back again. Yeah, and most of you guys already might know that I'm working on one project, and also you may know that I'm considering the embedded Linux as my primary OS. So today I have built a few of the kernel concepts, so I thought I would make a video on it. So even you guys also should able to understand why embedded Linux is more important and why it's being considered a lot in these recent days, and also why it's being called a friend of embedded uh, guy. Okay, so and if you guys are really interested in learning something new with respect to embedded, then please stay tuned till last, and if you come with some other background, then you may skip the video, no problem. Okay, so without wasting much time, let's get into the real concept. Okay, and yeah, I'll let me open new file. And one more thing, if I want to tell the advantage of an OS, then I'll have to compare with this something else, right? So what I'll do is I'll compare the bare metal code with OS. Okay. So what happens in bare metal code is, let's say there is a controller or a processor. So user directly should go and talk with the register, controller register. You have user only should configure it. So let's say there will be hundreds of functions. So these functions will share a common memory, common stack pointer, common program counter, common special purpose register. Okay, this we basically called as a task control block because a single guy is responsible for doing 100 things. Then obviously it will create a delay, or it will not meet the efficiency which you are expecting. That's why we will go with an OS. In OS, what happens is there is a processor and there is a user, and in between there will be a OS comes come. Okay, so this guy will take care of all the hardware model. User just have to make use of the special APIs and just run his code. OS will take care of each thing. How OS can make you to have the parallelism is by using the task or thread concept. Okay, let's say there are task 1, task 2, task 3, task 4. So these all four tasks has their own task control block. Task 2 has its own TCB, task 3 has its own TCB, task 4 has its own TCB. So obviously if somebody is dedicated to do only one thing, one job, then obviously the end product of him would be good than the guy who got more responsibilities, right? So this is how OS would be said it is more efficient. I mean, it can be more efficient than the bare metal coded one. Okay, so you may be wondering like, oh, what is the stack pointer, what is the program counter, what is the special purpose registers, why they are important, what they will actually help. You may be having a doubt on it, so let's clarity. I mean, I'll little bit give some glimpse on it. So what is the stack pointer? There will be a stack memory. The first top of the stack memory will be pointed by the stack pointer, and this guy will hold the return address of an API. Let's say there is a function called int sum a equals to b and return a plus b. So this return address will be held by the stack pointer. Whenever let's say there is a sequential flow of a code, and there here few of the APIs are running. So one this API is finished, where should it go, and where it should go and continue its execution will be taken care by the program counter. Okay, program counter will basically load the next instructions to the CPU or SP. Okay, so because of that, program counter is also an important concept, because it will load the next instruction to the CPU or PC. And like that, there are few other special purpose registers like LRU. All those things will come. If I tell those, it will take at least 1 hour to explain them. Okay, Now you guys know that why parallelism or multi-threading is not possible for a bare metal program one, and why it can be made possible in the OS. You guys, I think you guys aware. So now let's talk what is task. A task is some piece of a code which go who got his own TCB. TCB in the sense who got his own memory, his own stack pointer, his own program counter, so he can run parallelly, so he cannot wait anybody to get released, anybody to release his resource, all those things he cannot work and he cannot wait most of the time. Okay. And let's say you the processor you are using has only one core, so that case if you want to have the parallelism, then you have to go with an OS, or else it's never possible. If you are having multi-core processor, let's say there are three cores, and if you can have a parallelism by making use of the three different cores. One thing you run in one core, and second thing you run in one more, third thing you run for other functions. Like that, you can have the multi-threading. But if you have a single core, then you have to make use of the OS and make use of the task, and use it for the multi-threading option. Okay. So how multi-threading happens is, let's say there will be three tasks: task one, task two, task three, and consider four tasks. Okay, now this task is responsible for some CAN, this task is responsible for video streaming, this is for image processing, this is for recording something. Once this guy, I mean, let's say CPU is working on this guy, all the resources of a CPU is held by this guy, and this guy comes in between saying, hey man, I have to finish my work, it's important. Like that, if this guy come, it raises its hand, then there is a concept called context switching. Okay, it will store the context of a task, all the TCB of a task. Right, what is TCB? That is stack pointer, program counter, special purpose register. All those things will be stored in a priority queue, and it will hold this task, and CPU will give its resource to the task 2, and it will let the task 2 to complete, because that guy is more urgent, right? So he has to finish his job. That's why. Now once this guy is done with his thing, then again task status will be fetched from priority queue, and it will be continued. The task one things will be continued like that. It I mean it never be a parallel, but it will switch its context within very short span of time. So for user, it seems like an everything's are working in parallel, because it switches in the nanosecond time. So it make the people the one who are using, right, they see yes, things are happening in parallel, but it never be a parallel if we're working on a single core project, single core controller. Yeah. Okay. So how to create a task? Creating a task. So to create a task, there is a special API called pthread.create. Okay. To the API, we should pass pthread process ID and your API, and pointer size, memory size, and you have to pass your parameters of a API. Okay. So once you're done with the pthread dot create, it will create the different task or threads, and at last you have to make it pthread dot join, pthread join, and you have to pass your thread ID. If you don't call pthread join, what happens is in the processor there will be worker threads and main thread. If you don't call pthread join, then main thread will think that there is no worker thread, I haven't assigned any work to him, so I don't have to wait anybody to finish, I'll go and finish my work. Bhad mein jao, the other guys, like that it will think. But if you call the pre-thread joins, then you would tell your main thread that, hey, you have assigned something to your worker thread, let him finish his job, then only you finish your work, or else you have to wait for him. Like that, you will be telling your guy. Okay, that can be made possible by calling the pthread.join API. This is one thing. And as I said, there will be hundreds of tasks, right? Okay, so we don't know. I mean, if I say my daily routine, okay, not I don't consider my daily routine. Let's say there is something like uh, I'll I will log in when after I reach office, or I park my bike after I reach office, or what example shall I give? Something should be done by I mean, what to tell, man? Uh, I mean, usually I have a breakfast in office. Okay, first I should reach office, then only I can have a breakfast, or else I can't have a breakfast like that. There has to be a synchronization between task. If first task finish, then only second task should take a CPU usage. It should not be like one guy is already doing something. I'll go and stop him, and I'll block his work, and I'll make use of his all the things. If you do like that, then definitely there will be crashes in your system. So to have a synchronization mechanism, there will be a semaphore, there will be a mutex, and in the semaphore there will be counting semaphore, binary semaphore, and mutex is alone. Mutex can be either 1 or 0, 0 or 1, but this guy can be anything. And this guy will be, I mean, let's say there are three APIs. If one API is acquiring the semaphore, then other two APIs can release it. But the mutex case, if whoever acquires the API, that guy only should release it. It's not like signaling mechanism. But in the semaphore case, anybody can access, anybody can release. It's not like that. Yeah. And I'll cover this mutex, semaphore, all these things in particular video. We'll discuss in detail how does it looks like, all those things, along with these IPC mechanisms also. Okay, so till that time, take care. झूठी माई थारो बाप झूठा, सकल परिवार झूठी, कूटता छाती, ओ झूठी कूटता छाती।